everyone. In this video, I wanted to give you a little bit of intuition for partial derivatives, especially in the context of physics, even more especially in the context of mechanical waves. And so in order to do that, I thought we'd sort of work through an example. So we're going to consider, consider a particular solution to the wave equation. So consider the wave described by y of x and t equals the exponential of negative x minus vt squared. So this is some solution to the wave equation, and so it describes some wave. You can maybe in the back of your mind throughout this video think of having a string that's maybe connected to a wall, and you're just going to send a little wave pulse down the string. So you could have that picture in your back of your mind. So one thing before we get going that I thought I might want to remind you of is, so this is a video about partial derivatives, and right away I'm writing down a function of an exponential, and so you might want me to remind you about taking derivatives of exponentials. So I'll start by saying, recall, the derivative of an exponential is the easiest derivative you could ever take. So if we have d dx of, let's say, e to some function f of x, you have to do the chain rule. And so you end up with df dx. But the derivative of e to the x is simply e to the x. So the derivative of e to f of the x, you just carry along e to the f of x. So this is something that we're going to need throughout this video when we start to take partial derivatives. All right. So in order to get a feel for what this wave looks like, it's helpful to consider certain snapshots of it. So what we're going to first do is think about literally snapshots, so as though you were to take a photo of this wave at different times. So you're going to send this wave, and then your friend has a camera, and at certain times they're going to take photographs. So you're literally seeing the wave in position space. So let's first consider at time t equals 0. So what does this function look like at time t equals 0? This is equal to now e to plugging in 0 to the negative x squared. And you'll notice because we set t to some constant, this now just becomes a function of one variable. It's now just a single variable function. And we can plot it, and you'll see that it looks something like this, which if I were a better artist would look more symmetric, but you get the idea. So if you were to take a photograph of a wave that satisfies this equation at time t equals 0, it would look something like that. And then this wave is traveling down the string, and so if you considered some later time, so let's see what that would look like. So the height function x, now let's just say t equals t1. Doesn't really matter what time it is, some later time. This is now going to be e to the negative, so plugging in t1 for the time here, x minus vt1 squared. So now we know that it's been sent down, so now maybe it's over here. Again, this is as if you took a photo at some later time t1, and of course how far down it is depends on exactly what t1 is. So a lot of the plots that you've been looking at in studying waves aren't in position space, but are instead plots of one particular point on the string, and it tells you how that point is changing in time. And so we can alternatively consider, for instance, so let's consider just this point on the string at exactly x equals 0. So now we could write our function y of x equals 0, but now we want to see what happens to that point x in time. And so again, now plugging in 0 for x, this is the exponential of negative vt squared. And again, we see this is reduced to a function of only one variable. But now it's a function just of time. And again, we can plot this. And we'll see that it looks pretty similar to this one, but now we have this factor of the velocity. And so that's going to cause it maybe to be a little more spread out. I don't know, depending on what the velocity is. And now this is a function, this is a plot of time versus the height y. And then again, we could maybe consider some different point. So let's say we want to consider this point x1 and see how that changes in time. Now our height function is given by y of x equals x1, and now time is varying, and so this is e to the negative x1 minus vt squared. Again, it's now only a function of one variable because x1 is some constant, and we could plot this. And so trying to be consistent, so x1 at time t equals 0 was somewhere up here. And then as the waves moves to the right, the point x1 is going to actually increase. So we'll see that it looks something like this. So again, so this is telling us how the point, sorry, that should be a y, how the point at x1 changes as a function of time. So there are all of these different sort of pictures. If I could draw in 3 dimensions, we could actually draw all of these on one plot, but I'm not very good at drawing in 3 dimensions. So it's easier to look at these snapshots where we're reducing the function to a function of only one variable. So this is all great. We've learned a lot about this particular wave that we're studying, but maybe we want to quantify other aspects of this wave. So for instance, over here, you might want to know about sort of the shape of this, so things about the slope, for instance, or you maybe want to take it further and consider the curvature. So for instance, the slope, at this point, you want to know about that. So we know that the slope is given by the derivative. So the slope of all of the points on this curve, so the slope, so this is the slope of the wave, or the various slopes at different points, at time t equals 0. Remember, we're at a particular time. So that's going to be given by the derivative of y at t equals 0 with respect to x, which is just negative 2x e to the negative x squared. And then similarly, we might want to know what the slope is like at this later time. So the slopes, I guess, at t equals t1, our later time. So now again, that's just given by the derivative of y at t equals t1 with respect to x. And so now we have to take the derivative of this. Again, remembering t1 here is just some particular time, so it's just a constant. And so this is given by e to the negative, this is given by negative 2x minus vt1 e to the negative x minus vt1 squared. So this is some function that tells you about the slope at various points. And then over on this side in time, if we want to take the derivative of this function, this is going to tell us about the velocity of the particle, or the point on the string. So here we're considering, remember, only this point of the string at exactly x equals 0, and if we take the derivative of that with respect to time, that's going to give us the velocity. So the velocity of point x equals 0 is just the derivative of this. which is just given by, let's see, negative 2v squared t e to the negative vt squared. So this now, we easily in front of us have the velocity of the point x1 as it moves up and down as the wave passes by. And again, we could consider the different point x1, which is just some certain point. So sorry, the velocity dy dt for x equals x1, reminding us that x is just now a constant. We're just looking at some particular point, is given by negative, so let's be careful, 2x1 minus vt times chain rule. We pick up another factor of minus v times e to the negative x1 minus vt squared. So that's great. So now we know about, again, this is the velocity of the point x equals x1. So this is a video about partial derivatives, but so far I've just been taking single derivatives, or normal derivatives, and that's because all I did was take our multivariable function and reduce it to a function of a single variable. But what you'll see, if you understand partial derivatives really well, is that especially down here, what I've been doing is basically taking a partial derivative. So maybe in the middle of the board here. So if I were lazy, so this was a lot of work, right? I just did a bunch of different calculations here. If I were lazy, I would want to do it all in one go. And that's sort of what a partial derivative does for you. So if I don't want to, commit, I'm a non-committal person, I don't want to commit to some particular time t equals 0 or some particular time 1. I want to know about all of the slopes, and I want to leave t as a variable. You can do that. And you can learn about the slopes by taking the partial derivative. So what we want to do, if we want to learn about the slopes at all places, at all times, you just take the partial derivative. And so what you do is you say the partial derivative of y with respect to x. So if you recall, partial derivatives are taken by taking the derivative of y with respect to x, treating all other variables as constants. So we're going to leave t in there, but we're going to pretend temporarily as though it's a constant. And so what we get taking this derivative is minus 2 times x minus vt times the, maybe I won't write x because that's going to look like an x, times the exponential of minus x minus vt squared. So you can see this reduces to either of the calculations that we did before. If now we set it to time t equals 0, plug in 0 here, this reduces to exactly this expression. Similarly, if we plug in t1, we see that this reduces to this lower expression. On the other side here, if we want to know the velocities of all points on the string at all times, we want to be able to know all of this information. Now we take the partial derivative of y with respect to time this time. And so again, now we're taking the partial of y with respect to t. So we're varying t, but now we're going to keep x constant. So here we're going to pretend, we're going to leave x as x, but pretend that it's a constant. And what we'll see is that we get, actually, we end up with a plus 2v x minus vt times e to the minus x minus vt squared. And again, if we plug in the certain positions that we were looking at before, x equals 0 or x equals x1, you'll see that this exactly reduces to what we had before. So the partial derivative was just sort of a nice way of computing these things for these different snapshots, for instance, or for these particular points all in one go. And it conserves all of the information about different times or different locations. And of course, again, you could consider taking second partial derivatives. If you were to take a second derivative of this height function with respect to position, you're going to find that it tells you about the curvature of the wave. And if you took the second derivative of the height function with respect to time, of course, this was velocity, and that gives you the acceleration of the point on the wave. So hopefully this all gave you a little bit more intuition about what partial derivatives are doing for us. We're really doing exactly like what we were doing over here, where we were setting it to a particular time or a particular place. We're treating either time or place as a constant and then only varying the one variable. So hopefully that clears some things up. Of course, I'm always happy to answer any questions you might have. Thanks.